Hey everyone, welcome back to Probability Theory. This will be lecture 14 of the course. And in this section, we are going to discuss the expected value. So let's go ahead and jump into it. We'll call this section 2.3, the expected value. So in statistics, if you've had an introductory statistics course, you will know that we often talk about the average value or the mean value. So we often talk about the average or the mean value in statistics. Okay. Now, the counterpart to this concept in the probability theory parlance or probability theory world is what we call the expected value. So the expected value is the probability theory version of this. Okay. So let's go ahead and define the expected value. The definition here. Let y be a discrete random variable with probability function py. Okay. And so this probability function, remember, if you plug in a value for y, it tells you the probability that y will occur, right? And y being the random variable. Okay. And so that's the given. So then the expected value of y, and we denote it as e y, like so, is defined to be, well, it's very straightforward. Expected value of y is equal to the sum over all of the y's in that the random variable y can assume of y times the probability of y. All right, so you take the value of the random variable, you multiply it times the probability, and add those all up, and you get the expected value. So a quick example, just to solidify that concept. Consider this probability distribution. So I've got 0, 1, or 2 as the values that the random variable can take on. And the probabilities that correspond to those values are 1/4, 1/2, and 1/4. Right, so the probability of 0 is 1/4, probability of 1 is 1/2, probability of 2 is 1/4. So the expected value of y, right, is equal to the sum from y equals 0 up to 2 of y times the probability of y. Right, so you can just figure this out really quickly. That's 0 times 1/4 plus 1 times 1/2 plus 2 times 1/4. Okay, and so if you do all of that, you'll find that you get 1. Okay, and so this would be the expected value of this probability distribution. Right, and we can plot this distribution. So let's plot this. Let's say I'll put a 1/4, a 1/2, and 3/4. All right, and then what do we got? We've got a 0, we've got a 1, and we've got 2. So 0, the probability of 0, we can look here and we can see that it is 1/4. So it's, oh my goodness, so it's there. Apologies. And the probability of a 1 is 1/2. So it jumps up to here. Okay. No problem. And then the probability of 2 is 1/4 again. So that's down here. Okay, and so we can see sort of a visual presentation of this probability distribution. Now, if you kind of look at this, you can see that it's a symmetric distribution, right? Meaning the histogram is symmetric around the value of y, right? And so if you remember your statistic days, this is going to tell you that the mean or the average value for y is 1, right? So the average is 1. Okay. And of course, this agrees with what we calculate for our expected value, as we should. And so for that reason, we will typically say that the expected value of y, we'll denote it as mu, right? And it is virtually a synonym for the average or the mean. Okay. Now there's some distinctions there. The main distinction being that you're kind of crossing the line from probability theory to statistics, but you can, for most practical purposes, you can kind of think of the expected value as being like the mean. Okay, so let's move on. Now, occasionally, we may be interested in the function of a random variable and the expected value of this function. Right, so we may be interested in things like y squared or y cubed minus 3, right, where y is a random variable, or even the square root of y or something like that, where y is a random variable. So we may be interested in things like this, so i.e. functions of a random variable. So take a random variable and create a function out of it. Now an example of this would be something like the following, which isn't a great example because it's more like a continuous random variable, but that's okay, just to give you some context for why this may come up in the world. Let's let y be the velocity of a given molecule. Right, and so for various reasons, we may want to model the velocity of a given molecule as a random variable. It makes sense to do that. And so in physics, the energy impact by a moving body is actually proportional to the square of the velocity. So the energy impact from a moving body is proportional to the square of the velocity, right? So you may know this from your physics. So, if we're interested, if we're modeling if we're capturing the velocity of a given molecule using a random variable y, and the energy impact by a moving body is proportional to the square of the velocity, we, if we're interested in the energy transmitted by a molecule, then we would be interested in not y, but y squared. Our work may have interest, given this, in y squared rather than y, okay? And so maybe we're interested in the expected value of the energy impact from a molecule. And so in that case, we may be interested in the expected value of y squared rather than the expected value of y. Okay. So again, this is just kind of to lend some context to what's about to come. So you may say, well, why would I ever care about the expected value of some combination of the random variable, some additional function? Well, this is an example of where you might be interested in that. In fact, it comes up all the time. And so how would we go about calculating the expected value of something like y squared? Well, that is the subject of the next theorem. So let's let y be a discrete random variable. let y be a discrete random variable with probability function py. Okay. And then let g of y be a real valued function of y. Right, so I've got a random variable y, and I've created a new function g that incorporates that variable. Then the expected value of g of y, so now we're not taking the expected value of just y, but the expected value of a function of y, is equal to, very similar to the definition of the expected value of y, so it's the sum over all the values that the random variable y can assume of g of y times p of y. Oh, I should put this as lowercase. Sorry, apologies. Let's rewrite that. I want this to be lowercase. All right, so you plug the value of y into g, get a value out, multiply it times the probability of y. Okay. All right, and so for example, this molecule velocity question up here, if I'm interested in the expected value of y squared, what I could do is I could just say the expected value of y squared is just equal to the sum over all the values of y that the random variable y can assume of y squared times the probability of y. All right, now I don't have actual data for this, but you can see how you would do this. You have a bunch of values of y, and you presumably know all of the probabilities of those, so it's just a big sum. Okay. All right. Very good. Now, the proof of this is fairly straightforward. I'm going to leave it to you to look into. So the expected value of the expected value of g of y is equal to the sum over all the values that y can take on of g of y, p of y. Okay, so proof, that's on you. Right, it's not a difficult proof. The proof's in the book, but just in the interest of time, I think I'm going to skip over it. Okay. So from this definition of the expected value and from this theorem that the expected value of a function of a random variable can be calculated, we can get to the idea of the variance of a random variable. Okay, and so let's go ahead and define the variance. So the variance of a random variable y is defined to be the expectation, the expected value of y minus mu squared, where mu is the mean of y or the expected value of y. Okay. All right, so the variance of y is equal to the expected value of y minus mu squared. Okay, and then we say that the standard deviation of y is the square root of this. Right, so it's the positive square root of this. All right. Very good. And so this idea of the variance and the standard deviation is something, again, you will have seen in a Intro to Stats course. And so this gives you some sense for the spread of the data. Right? And we'll get into this in more detail later, but the standard deviation tells you how kind of spread out the data points are. All right, let's do an example here of calculating this. Let's say we have this probability distribution. So we've got a y and a probability of y column. And we've got 0, 1, 2, and 3. And our probabilities are 1/8, 1/4, 3/8, and 1/4. Okay, so we've got this. Let's say we want to find the expectation of y, expected value of y, and the variance of y. So we'll say that mu is equal to the expected value of y, which is equal to the sum from y equals 0 up to 3 of y times the probability of y. All right, that's just the definition. And so we can plug these values in. 0 times 1/8 plus 1 times 1/4 plus 2 times 3/8 plus 3 times 1/4. Right, so just kind of going through 0 times an eighth, 1 times a fourth, 2 times 3/8, etc. And that's what we get here. And then if you sort of crunch all these numbers, what do you get? You get 0 plus a fourth plus 6/8 plus 3/4. And if you do all of that, you should get something like 1.75 if you wanted to represent it as a decimal number. All right. Now the variance then, the variance, remember, is sometimes referred to as sigma squared. That's a symbol for the variance. That's equal to the variance of y. And the variance here is equal to, remember the definition that we just had, it's equal to the expected value of y minus mu quantity squared. Okay, and so we just found mu, so we know the expected value of y itself. And so this means this is equal to the expected value of y minus 1.75 quantity squared. Okay, now unfortunately, the expected value is one thing. The variance can be quite a bit more computationally, just because now you've got this additional thing to do. You got to take, calculate a difference and then square it. So let's go ahead. This is an easy one because we've only got 4 values, but let's write this out. So again, just kind of starting with the definition, this is equal to the sum from y equals 0 up to 3 of, in this case, it'll be y minus 1.75 squared times the probability of y. So I'm just going to put those values down here. So that would be 0 minus 1.75 squared times the probability of 0, which is 1/8, plus 1 minus 1.75 quantity squared times the probability of 1, which is 1/4, plus 2 minus 1.75 quantity squared times the probability of 2, which is 3/8, plus 3 minus 1.75 quantity squared times probability of 3, which is 1/4. Okay, so you've got this like sum. And when you do all of that, do pause the video and try to calculate that, make sure you can get to that. You get 0.9375. Okay, and so that's your variance, or sigma squared. Then the standard deviation is equal to the square root of sigma squared, otherwise known as the square root of the variance of y. All right, it's kind of going through all the notation varieties you can come across here. And so that's just equal to the square root of 0.9375, which we see is 0.97 when we run the numbers. Okay, so that is an example of how to calculate the variance. And so you can kind of see the variance is really just, it's the expectation of a function of the random variable y, right? So that's why we kind of led with that theorem, and then we jumped to the variance. Now, kind of thinking about that theorem a bit more, there are a handful of properties that can be stated. So So there's a handful of properties that use this theorem, the expected value of a function of a random variable. The first one says that the expected value of a constant, unsurprisingly, is the constant. Right? And you can kind of prove this one easily, right? So let's just let g be a function of the random variable y that's equal to this constant. Then, of course, the expected value of c is just equal to the sum of over all the values that y can take of c times the probability of y. Right, now notice c doesn't change as a function of y. It's always c. And y varies, but c stays the same. So that means you can pull it outside of the sum. And you have this. And then, of course, what is the sum over all the probabilities of y? Well, that's equal to 1, right? And so we can see that the expectation of a constant is itself. All right, kind of related but a little different here is this theorem. Let's let c be a constant. Then the expected value of c times a function g of the random variable y is equal to c times the expectation of g of y. Right? Meaning, basically, you can pull constants out. You can factor a constant out of the expression of gy. Right? You can do that. And so the proof there, let's see, how would we do that? Well, we'll say the expected value of c of gy is equal to, let's do the summation here. This would be c times g of y times p of y. Right, now, of course, this is a sum, or the constant is in every term of the sum, so we can pull it out, and we just get this, which, of course, that's what we're after, c, and this is just the expected value of gy, right? And so that's pretty easy. These are just, again, just properties of summations. All right. One more. Well, two more, actually. Let's look at this one. All right, this one is, again, another property of just how sums work. Let's let g1 of y, g2 of y, and so on up to gk of y be k distinct, well, possibly distinct. They could be the same if you wanted. Let these all be k distinct functions of a random variable y. Okay, then, well, the expectation of g1 plus g2 plus all the way up to gk, so kind of thinking of taking the expected value of the sum of all these functions, that's equal to the sum of the expectations. So that's equal to the sum of the expected value of g1 of y plus the expected value of g2 of y plus plus the expected value of gk of y. Okay, so just like you would kind of expect this, right? You've probably seen things like this in the algebra world. Now you could prove this theorem. Let's prove this. I'll just give you the outlines of a proof for k equals 2. And then I'll leave it to you to prove it for sort of general k. But for k equals 2, I mean, you can think about how to do this. It would just be the expected value of g1 of y plus g2 of y. Right? And let's just write it out. That's equal to the sum over all the values that the random variable y can assume of g1y plus g2y times the probability of y. Right? Just looks like this. Okay. And we know that we can distribute the probability of y through these parentheses here, and we would have the sum over y of g1 y py plus the sum over y of g2 y py. Okay, and then of course this is just the expected value of g1 of y. This is just the expected value of g2 of y. And so that means we've got what we wanted here. So g1 of y plus the expected value of g2 of y. Now you could, that's not really a proof, this is a proof for k equals 2, but you could extend this to any k, and you can see obviously how that would work. You just have more things in the sum. Okay? Or just make the number be just arbitrary, just ... up to gn. So give that a try. Okay, very good. Let's do one more theorem, one more important property. This is something that will come up all the time, and so it's important to talk this through. And that's this one. So the variance can be calculated in the way that we've seen already, but there's another way to calculate the variance, which is oftentimes very useful. Let's let y be a random variable with probability function py. So I'm just going to write RV with probability function py. Okay. Then the variance of y is equal to, okay, we can say it's sigma squared, which is equal to the expected value of y minus mu quantity square. This is the one we've seen before, but this is actually equal to the expected value of y squared minus mu squared. So the variance can be calculated using this technique here, this formulation of it. Or instead, what you can do is you can identify the expected value of y squared. So if this only works if you know the expected value of y to begin with, right? So if you know the expected value of y, which you probably do if you're going to do it this way, right? So if you know what mu is, you can calculate the variance using this technique, where all you're really doing is calculating the expected value of y squared and summing from all of that the square of the mean. Okay. So why does that work? It's actually very straightforward, but let's just see this. So if I start with the variance of y equals this, then I could just do the algebra here on the inside here, this y minus mu quantity squared. I can FOIL this out, right? And when I do that, I get y squared minus 2 mu y plus mu squared, right? Just FOIL, first outside, inside, last on that one. And I get this. And then, of course, from what we saw before, I can kind of break this. I can think of this as G1, G2, G3. I can kind of break this up. And so I'd get the expected value of y squared minus 2 mu times the expected value of y. Again, I'm pulling, these are constants, so I'm pulling them out, plus the expected value of mu squared. Okay. Now, this is a constant too, so I probably should have done that in the last piece, but let's go through that. Minus 2 mu expected value of y plus mu squared. Right, that's just a constant, so the expected value of a constant is a constant. Now, the way this works is you just recognize something about this expected value of y. So note, expected value of y is mu. Okay, and so I can rewrite this as the expected value of y squared minus 2 times mu, right? That's this, and then plus mu squared. And so, of course, that's expected value of y squared minus 2 mu squared plus mu squared. And so these can be combined, and you get minus 1 mu squared, right? I got 2 minus 1. So this is the expected value of y squared minus mu squared. That is what we're after. Okay. Very good. And so that's something that's really useful, and we'll see it throughout the course. It'll come up a lot when we're trying to calculate. When we're writing proofs or we're trying to derive something and we need to rely on variance, oftentimes that's useful. It's also useful just in practice. It's more straightforward just to calculate the expected value of y squared if you already know mu, right? Which you almost always do. So, okay. Let's do an example here, kind of a more practical example. Let's say, and this is an example that involves the expected value. Like, when is this useful? What kind of things can you get to from this? So a game costs $2 to play. Okay. And what is the game? Well, you roll a 6-sided die. You roll a 6-sided die, and if you roll a 6, you win $10. If you roll 1 through 5, you win $0. Okay, so it's basically like a really super basic gambling game, right? Like where you just roll a die. If you get a 6, hey, you win $10. If you don't roll a 6, you win nothing. Okay, and so let's define a random variable x to be the net profit from playing the game. Okay, and what do we mean by the net profit? Well, basically, x is equal to the winnings minus the $2. Right, so I got to pay $2 every time I roll the die, right? I could win or I could not win. X is the difference between those two. So it's the net profit. So let's find the expected value of x. Okay, so we want to find expected value of x, and let's also find the variance of x. Okay, so to do this, let's think about kind of the probability distribution first. So what are, you've got outcomes, right? And so you could say the outcomes are 1, 2, 3, 4, 5, or 6. But in the context of what you win and the random variable x, there's really just 2 outcomes. Either you roll a 6 or you roll 1 through 5. Okay, now if you roll a 6, what do you get? Well, you get $10. If you roll something else, something other than a 6, what do you get? You get $0. Okay, and so the random variable x is the net profit. And so x, what is x if you roll a 6? Well, it's $10 minus $2, so it's $8. And what is x if you roll something other than a 6? Well, then it's $0 minus $2, so negative $2. Okay, there you go. And what's the probabilities? Can we do this as a fair die? Okay, well, in the case of rolling a 6, well, it's 1 out of 6, right? So 1/6. Okay, pretty basic. And anything else is the rest of it, right? So 5/6. Okay, so this is kind of like our, this isn't exactly what we would want to put as for our probability distribution, but like you could summarize this and get a nice distribution. You get x and probability of x. X is either 8 or negative 2. Okay, and then the probability of getting an $8 net profit is 1 in 6. The probability of negative 2 is 5 out of 6. Right, so at the onset, it's like, well, if I win, I do get $8, but if I lose, I get negative 2, right? So there's more upside in the terms of like my winnings. It wouldn't be really worth doing if it was 2 and negative 2, that's for sure, right? But the probabilities kind of offset this a little bit. And so really what the expected value is going to tell us is like, what should we expect to win each time we roll this, right? And you can use that to kind of think through whether this game is a good game to play or not. So what is the expected value of x? Well, just using the definition, this is going to be the sum over the x values times x of x times px, right? Okay, the x values are 8 and negative 2. And so that you can't index that nicely, so really it's just the sum over all the valid values of x. And so that's $8 times 1/6 chance plus negative $2 times a 5/6 chance. And so this is like 8 minus 10 over 6, right? And so negative 2 over 6. This is negative 1/3, which is about negative 0.33, so about 33 cents per play. So on average, you will lose about 33 cents per play of this game. Right? So does that mean, given that information, like, should you play this game? No, you shouldn't play this game. Like, even if you play it 100 times, you're going to lose on average 33 cents per time. You might win one, but you're not in the long run, you're going to lose money playing this game. Right? The odds are just, that's what we mean when we say the odds are stacked against you. The probabilities are not in your favor. Right, as the player of the game. Now, if this is a game you can convince others to play, you will probably make money. But in general, you won't make money playing this game. Now, what about the variance? The variance here, well, that's equal to the expected value of x minus mu quantity squared. Okay, we could also calculate it as the expected value of x squared minus mu squared. All right, so you can try it both ways. I'm going to do it the old-fashioned way, but then I'd like you guys to try it this way just to confirm that you get the same answer. All right, but I'll just go through the values here. I'll take 8 minus negative 0.33. The mu here is negative 0.33. Okay, so 8 minus negative 0.33 quantity squared times 1/6, that's the probability of getting $8, plus negative $2 minus negative 0.33 quantity squared times 5/6, that's the probability of netting $2 on a game play. And when you crunch all these numbers here, you'll get 11.56, and here you'll get 2.32, and so together you should get something like 13.88. So that's the variance. So what does that variance mean? Well, you can see really from the variance that the outcomes fluctuate pretty wildly, right? So on general, you'll typically lose $2, but occasionally you will win $8, right? So about 1 in 6 you'll win $8, and the rest of the time you'll lose $2. So that's a pretty radical difference, and so that's why you do see such a significant amount of variance here relative to the values involved, relative to the mean especially. All right, very good. So that's a good place to end this one, and then next time we will start to get into some special distributions. We'll spend a fair amount of time on those. Those are very interesting. So next time we'll start getting into special distributions, and we'll start with the binomial distribution. That'll be next time. All right. Until then, take care, everyone.